All right, so last time we learned that kinetic energy is equal to 1/2 times mass. And what was the symbol again, right? This is mu, this is velocity. So there's going to be kind of some plug and chugging type of problems, but first we kind of have to derive some new equations. So we're going to say that we have 1 mole of gas here. And so if you think about the mass of 1 mole, it's going to be the same as the molar mass, because you only have 1 mole of it, and molar mass is grams per 1 mole. So we can sub that out into mass. So we can say kinetic energy is equal to 1/2 times this molar mass times mu squared. And then there's another equation for kinetic energy that relates kinetic energy to temperature. So it's that kinetic energy is equal to 3/2 times R. We'll learn about this R in a bit here, times the temperature. The temperature, of course, must be in Kelvin. So you can see both of these equations are equal to kinetic energy. And of course, kinetic energy is equal to itself. And so we can take these guys and plug them in and substitute them in here. And so these two must be equal as well. So 1/2 times molar mass times mu squared is equal to 3/2 RT. And so if you kind of reorganize this equation, you can solve for the root mean square average velocity, right? So if you do all the algebra, you get 3RT over molar mass, right? So this is molar mass, but it has to be in kilograms per mole, kilograms per mole. So it's different than what we've been doing before. So you have to go from grams to mole to kilograms per mole. And this R, it's still the same gas constant, but now it has a different value. And that's because it has different units. Here we're talking about 8.314 joules per mole Kelvin. Joules per mole Kelvin. So you can see we're talking about energy because we're talking about kinetic energy. And so basically what it works out to is that another way you can rewrite this unit is in kilogram meters squared over second squared, because that's what a joule is. So joule is all of this stuff right here. And then you're left with the moles K as well. And so see if I show you that next example. No, I don't. So the units do work out, but if you try to plug in the units from the beginning, you're going to see that they're going to look a little funky, and that's because you're not using the old R, you're using this other R, which is in units of joules. And so if you think about the units here, let's just take a look at the units. The number 3 has no units, so we won't have any units there. Your R here, again, kilogram, meters squared, second squared, moles, Kelvin. Your temperatures has to be in Kelvin, and then down here, you're in molar mass of kilograms per mole. So if you think algebraically how all this is going to work out, these kilograms are going to cancel out, these moles are going to cancel out, and then these kelvins will cancel out. And so then when you take the square root of this, the units will end up in meters per second, right? And since we're talking about velocity, that makes sense. Velocity is how quickly something travels in a certain amount of time. So in this case, in meters per second. Let's take a look at an example. So example question might be find the root mean square velocity for nitrogen at 30 degrees Celsius. So a couple kind of little tricks to this problem. First of all, let's go ahead and write out our equation. The root mean square velocity is equal to the square root of 3RT over molar mass in different units. And then let's think about this a little bit. Nitrogen, you have to be careful here. Nitrogen is a diatomic gas. So when someone says nitrogen, they really mean N2. They don't mean nitrogen by itself. And so if you look up the molar mass, that's 28 grams per mole. But remember, this molar mass has to be in kilograms per mole, in kilograms per mole. So you need to actually convert this to what would end up being 0.028 kilograms per mole. And then if you think about the 30 degrees Celsius, this is going to have to obviously be in Kelvin. So we're going to add 273.15, which will end up as 303.15 Kelvin. Our R here, be careful of the R. This is going to be equal to 8.314 joules per mole Kelvin. Or you can think about it in terms of these kilograms meters squared per second squared as well. And so if you go ahead and plug and chug through that, you get 520 meters per second, which is quite fast. So if you look that up on, change it to miles per hour, you get about 1,100 miles per hour. So a molecule of nitrogen gas at 30 degrees Celsius, that's not much more above room temperature, is moving about 1,000 miles per hour. Pretty cool.